All right, and the story continues. Welcome back to 10.3 Sequence and Series. This is Mr. G here, and I'm going to help you lead you guys through some topics today, which are going to be we're going to move into the geometric sequences and series. We're going to talk about, instead of arithmetic ones, we're going to talk about geometric sequences and series. So, again, we're not going to do any of the review stuff that's up at the top, and we're going to move down to talk about a different kinds of series that or sequence that we didn't do last time. So this time around, the last time around, let's just say at 10.2, we were really focused on doing what was called an arithmetic sequence. And those arithmetic sequences that we were focused on had a common difference concept, and those common differences were based usually on addition or subtraction. Okay, so we had two formulas that were associated with those. Now in 10.3, how this is going to end up changing is, of course, as we do most of our stuff in mathematics, when we talk about stuff that's based on addition or subtraction, then it makes sense that the next operations that we should basically talk about are going to be multiplication and division. And those particular sequences that are based on multiplication and division are called geometric sequences. And instead of being what's referred to as a common difference between the two numbers, now there's going to be, in a geometric sequence, the list of numbers are separated by a common ratio between those two ideas. So we're going to use R. And those ratios are going to be basically understanding how the sequence is based on multiplication or division. Now, I don't really like to say division, because what it's really based on is multiplication. Even though we might be multiplying by a number like 1/3, it is really still a multiplication, even though it's actually dividing those numbers. So let's try and find out what we should do with sequences that look like that. And then later in the notes, we're going to talk about how do we use the series of those particular ones if we put plus signs between everything and summed everything up in terms of how much does it all do. Now, what you really want to do first is, when you look at a sequence, you've got to make a determination of which category are you in. Are you arithmetic or are you geometric? Is stuff going up by addition or subtraction, or is stuff moving around by multiplication or division? So the first thing we're going to do is take a look at a sequence like listed right here, and we're going to try out, and I always try out the common difference part first. And if you don't see a common difference that's being the same, then it must be that you can check that box and say, oh, it's not that kind. So if I was looking at this the first time, it'd be like, oh, it goes up by 3, and then it goes up by 6, and then it goes up by 12. Well, those common differences don't make any sense when it comes to arithmetic. So you'd be like, okay, it's not arithmetic in any way, shape, or form. But what is going on between one term and the next term is that you can see that the previous term is being multiplied by 2, and then it's multiplied by 2 again, and then times 2 again to keep going up the sequence. Now, this is a clear sign that it has a common ratio. And that common ratio means that it's going to be geometric and not going to be arithmetic. Now, to find a common ratio, really simply, once you see that it's based on multiplication or division of some sort, a common ratio can easily be found by using this little formula right here about what the ratio is. Now, that is written in a recursive format. I always like to think of it as that the common ratio is the second term divided by the first term. It's going to give you a number of how much that thing is being multiplied from term to term. I always like to do 2 divided by 1. You could do 3 divided by 2 or 4 divided by 3, whichever term you want inside the sequence, but it's got to be 2 successive, the one further down the line divided by the one previous. And in this particular case, it would be 6 divided by 3, and you can see that the common ratio is 2. Now, this common ratio is just as important as the common difference was to arithmetic. So you can use that common ratio to help you find terms that are down the sequence. Now, if you have to find one that's just the next one in line, you're like, oh, okay, if I've already got the sequence and I want the 5th term, a sub 5, I could go to the sequence and I could just basically plug in that it's multiplied by 2, and that'd be the number 2 times 24, and I'd get the number 48. Seems relatively reasonable. If you're really close to that particular term, just apply the common ratio and you're ready to rock and roll. But if you're further down the line and you're trying to figure out the 13th one, now the last thing you want to do is build these geometric sequences all the way out to several terms out, because unlike arithmetic ones, they get big or get small really, really fast. So we've got to kind of think about, how are we going to get the 13th term? Well, there's going to be a couple things we have to consider. Number one, just like we did in arithmetic, you're going to have to ask yourself, where does the actual sequence start? Well, this particular case, a sub 1 turns out to be 3. You have to have a starting point so that you can determine where 13th term is going to actually be. And it probably has a lot to do with what's going on with the ratio. How much am I really multiplying by to get to the next part? Well, the ratio in this case is the number 2. Now, the part we want to figure out is, how many times is that common ratio actually being applied? Well, if I looked up here for the 5th term, the 5th term was listed right here. The common ratio is being applied once, twice, 3 times, 4 times. And it turns out that if you want the 13th term, you would apply this common ratio 12 times. And the reason behind that is you're going to apply it to get to number 2, and then you're going to apply it to get to this 3rd one, and so forth. You'll do one less than that amount. Now, if I had these pieces of information, I might be able to write a formula that would help me find the 13th term. That 13th term, or a sub 13, has something to do with it starting at 3, and then it's going to get multiplied by the common ratio, which would give you the next term, which is number 6, but you're going to common ratio this thing 12 times. And this particular answer would return what the 12th term or 13th term is, which happens to be 12,288. Holy moly, that thing's huge. Okay, so you've got to be really careful in how that particular aspect comes out. Now, if I apply that same kind of basic knowledge to, say, like finding the 113th term, then it must be something to do with, where did it start? Because that's super important. Got to lock it in. And then how many times did I apply the actual ratio to it? Well, I didn't apply it just once. I applied it 112 times, or 2 to the 112th power. Now, that actual number turns out to be 1.56 times 10 to the 34th power, written in scientific notation. I'm going to say approximately. And that number is freaking big. You're really big. Okay? Big, big, big with lots of G's on it. Okay? Oh, I'll put even a G in quotes because that's the way I like it. Okay? So geometric sequences get relatively large really, really fast. Or they can even get really super small, depending on how the geometric ratio or the ratio works. Okay? Now, if we wanted to put this into some like generalized formula, we should be able to kind of write a geometric sequence, or better yet, what's referred to as an explicit formula that would allow us to get to any one specific term. This is your zip kind of function that'll get you there. So if I wanted a sub n, whatever the function is where I want to get to, 113th or 13th, I have to absolutely take the first term, a sub 1, and multiply it by the common ratio raised to, and this is always one less than the term that you want to get to, because it's how many times you got to apply the common ratio, or n minus 1 in the power. This is a formula for the geometric sequence explicit term. Okay, get that one in your brain. You want to come back and use it multiple times. Okay, now let's try a couple of examples, and then I'll turn you loose on a couple that you can try. Write the first 4 terms of the sequence. Now, writing 4 terms is really not that hard. It says to start the sequence at 1.5. And then it's saying that the common ratio This is your multiplier. Remember, we say common ratio, not common difference. It's a multiplier of what we should multiply each successive one by. So this one times 2 would be the number 3. And then if I multiply that one by 2 again, I would end up with the number 6 and then the number 12. Okay. Now, to point out the reason why this particular deal is a geometric sequence is because it's based on multiplication. And if I really thought about this kind of like as a graph too as well, and I'm just going to back one of these guys up because this is like term number 1, and this would be term number 0. If I backed it up and divided, I'd end up with like 0.75. I could actually start to graph these like 0 and 0.75 and 1 and 1.3, and 2 would be the number 3, and 3 would be the number 6, and you would probably recognize that the pattern is exponential. And that's why the equation itself is an exponential function as well. So when we say geometric sequence, we're really focusing on numbers that are based on an exponential either growth, or sometimes they can be even exponential decay. All right, so that kind of leads us to some old stuff that we've seen in the past. All right, now, hold on, I gotta turn my control key off. I don't know why it's on. Now, number 2, let's try it again. Let's find the first 4 terms of a geometric sequence if it was written as, okay, 1 is the first one, but oh man, they changed it and wrote the equation as a recursive style. Now, that doesn't make any difference. It just means that recursives can be done exactly the same way. They just have a different little format. And what it is it's saying take the previous term, the one in the past, and multiply it by -3, and you get the one that's in the present. Well, if I take the one that's in the past, multiply by -3, I get -3. Then now this one becomes a past, and the next one becomes a future. That'd be 9. And then multiply it again by -3 would be -27. Now, funky thing here is if the common ratio is a negative, it will alternate like that. If it's a negative integer, it'll alternate. If it was a negative fraction, it'd alternate and go down. It's just, you got to look at how each sequence works out. Okay. Now, specified using the formula that you used above, I'm going to give you guys a chance to try example number 3 and example number 4 on your own. So pause the video at this point in time and try and find a sub 17 and a sub 21. And there's all the answers right there in front of you. Shazam! Okay. I promise you I haven't been drinking. Okay, now let's take a look at what you came up as possible answers here. First off, they give you the first term. That a sub 1 goes out in the front. Notice that it's a coefficient. And it's the common ratio that becomes the exponential base that we raise the power to. And keep in mind that you want to raise it to 1 less than the term that you're on, because that's how many times the exponential gets applied. So 78,643.2, woohoo, sounds like a good answer, okay? And as you'll notice, these numbers, they get relatively big really super fast. Number 4, original term -2, then the common ratio is 0.5. Now, we haven't really seen one like this, but if the common ratio is less than 1, we're talking about something that's less than 1, then that must mean that it's going to shift gears from being a growth concept to being something that's based on decay. So now you can see the relationship that those exponential rules that we learned earlier do end up applying to the same kind of idea in geometric sequence. So we would expect that this number not to be really, really big, but to be relatively small. Okay, and that is exactly what the number turns out to be. A super small number, 10 to the -6th in terms of scientific notation. Now, if you get numbers that are like this on your calculator, pay attention to what the Math Excel asks you to find and how they want you to supplant that. If they want you to round it to hundredths, so follow directions on those. Maybe this might be something that Miss Merzak might tackle and make sure that there are no problems on this when it comes to the Math Excel. Check those things out on the Math Hints videos too, because they've been really helpful in the past, and they can help you get a really good grade on your Math Excel. Okay, let's move on to the next page right here and see if we can tackle a couple more of these. Now it says write the general formula for each one and then find the specified term. Now in the last ones, they gave you the first term and they gave you the ratio, but this time around they want you to find the 18th term, and they're going to take something away from you. They're just going to give you the sequence, and they're going to go, okay, well, first off, I know that a sub 1 is going to be the number 4, but the common ratio is missing in this particular formula. I know I got to raise it to the 17th power. So how am I going to find that common ratio? And that little simple formula at the beginning that we first talked about to find that common ratio is easily found by taking the second term divided by the first. And in this case, it would be 6 divided by 4, or 3/2 would be your common ratio. Now, if we take that 3/2 concept and plug it in, we could come up with the answer to this particular question. Now, I'm going to plug this one in my calculator, make sure that we all understand how the operation should look in your calculator. So we're talking 4 times, and if you have a fraction on this one, do the 3/2 in its own set of parentheses, and then use your caret key to raise it to the particular power that you want. So make sure that you're plugging in values correctly. So this ends up turning out to be 3941.05. And I'm rounding most of my stuff to the hundreds place, but again, read directions to make sure that it works. Okay. Sometimes a geometric sequence, instead of going like this one, which is going up in a growth concept, sometimes they go in a downward spiral, where they're headed in a negative direction or a down direction. And sometimes they alternate signs too as well, where it goes positive to positive to negative, negative to positive, and so forth. So let's see what we would write in that particular case. No real difference. A sub 12 is going to end up being the first term, the number 3, multiplied by the common ratio raised to the 11th power. Now, we'll still write to that common ratio deal, take the second term, -1 divided by 3, and you end up with -1/3 being your common ratio. And that just means that since the common ratio is less than 1, we would expect that this particular function would be headed in a downwards direction. So 3, -1/3. Again, make sure you're using your negative key correctly and not using the subtraction key, and raise that to the 11th power. And you would end up getting a really super tiny number, which is -1.6 or -1.7 times 10 to the -5. Okay, small number, and that's what we expect, is it's getting super, super small. Okay, now sometimes you might get these sequences that go on, but they don't want you to necessarily find just the sequence's terms. They want you to find the sum of the geometric sequence. Now, if you think that a geometric sequence goes up fast, a geometric series or sum has to go up even faster, because you're adding up all those numbers that came before. Now, this particular formula I'm not going to derive for you, but I'm going to write it down so that you know what it is. It's a sub 1. You have to have a place to start, and then that comes from 1 minus r raised to the n, all divided by, and this is probably one of the harder formulas to deal with, 1 minus r on the bottom. All right, and that is your formula for finding a sum of a geometric sequence. This is one of those 4 formulas that you really want to get. You want the arithmetic, sequence, and series, and you want the geometric sequence and series formulas in your back of your brain so you know what you're doing. Okay, now read the question carefully. It says find the sum of the first 24 to 21 terms of the sequence. Well, that sum of the first 21 terms is going to be a sum of 21 terms, but you have to plug it into the formula correctly. And in this particular case, we're going to use the first term, which is the number 2. And then we're going to keep plugging in here. 1 minus, now I got to get stuck right here at the ratio. The ratio is going to be very important in this. And we're going to find it by second term divided by first. 6 divided by 2, which is 3. And that's going to be 3 raised to the 20th or 21st power, and then it's going to be divided by, all divided by 1 minus the rate again. Now, the key to these is to make sure you stay consistent with how you plug them in. If you plug them in correctly, you can ultimately make a mistake in terms of what the number is. My biggest key here would be do the top first and then do the bottom second. That's the easiest way to plug these guys in. People who try to plug it all in one shot, they end up screwing up their parentheses, and it ends up being ugly for them. So 1 time, or 2 times, 1 minus 3 raised to the 21st power. Now, once you're done with that actual power, come back down and close your parentheses. Now, like I said, I like to do this number as its own separate entity. That's the numerator. Whoa, times 10 to the 10th. And then I'm just going to divide this answer by -2, which happens to be the answer for the bottom. So the answer is 1.04 times 10 to the 10th power. Ooh, that's really ugly. Don't look at that. Okay, so a really big number is what my expectation would be. Now, you could probably train your calculator to do the same kind of question, but to do it in what's referred to as a sigma notation. Now, sigma will again sum things up just as easily as anything else, but that is basically summing up 4 raised to the first power, and then 4 raised to the second power, and 4 to the third power, and so forth down to 4 to the 7th power. Now, I don't want to do that by hand. That's a pain in my butt. Okay, so maybe a sigma on your calculator could easily do the same kind of process. Now, let's see if I can come up with that. That would be under math and summation. And then it's going to ask us for a variable. Let's call it x. And we're going to go from 1 to 7. And inside here, be very careful about how you plug this in. I know that the way it's written in the notes, it's 4 raised to the x. But I'm going to put the 4 raised to the x inside, because if you put it on the outside, it thinks of it in a different location. So it's got to be, where am I plugging in the x inside of that summation? The summation should have its own set of parentheses. And that answer turns out to be 21,844. 21,844. See if you can recreate that and give it your own deal. Now, could it have been possible to do this one before with a summation function too as well? And yeah, you really could have. You could have summed up, in this particular case, x is equal to 1 going from 1 to 21. And then right here, you would have to write an explicit formula for the function. Now, the cool part is you know that explicit function already. It's the same one we discussed before, which happens to be a sub 1 times r raised to the n minus 1. So I'm going to put right here that the first term of the sequence was the number 2, and multiplied by the common ratio, which is the number 3, raised to the x minus 1. And that explicit formula plugged into the sigma would give you exactly the same answer as the 1.04 times 10 to the 10th. Try it out. I bet you it comes out being the same way. So you can see that the sequence and the sum, they work hand in hand. So if you want to use your calculator, that's a possible idea. Now, there's something strange that happens with sequences and series, specifically series in geometric. And what I'm going to say here is what if the geometric series goes to infinity? Now, your first thoughts would be, well, of course, if the sequence goes to infinity, it should end up being infinity, or if even it was going down, it seems like it would be negative or positive or negative infinity. But there's a caveat here. If it turns out that the series has an infinite number of values, but its common ratio is between 1 and -1, meaning that it's a fraction of some sort, it's being divided, so it's kind of going in a division kind of sense, but it's not going to divide to negative infinity. It is going to converge. Now, this is a good example. This concept is going to mean, I'm going to put here that it converges, okay? Or better yet, it approaches a limit, okay? Now, here comes your very first concept of calculus about limits, about meaning that it goes to a number. And it's strange to think that if something continued on to infinity, that it would more or less coalesce into a value. Okay, and that is one of the big things that calculus will help us try to explore is what happens when we get really close to infinity or negative infinity or really close to a number but not quite there yet. Now, if I start to consider this about these numbers being added up, you can definitely tell that right out of the gate, you're like, man, it's definitely more than 4. Okay. But then if I add on just a little bit more, you're like, well, man, it's a 4 and a third. And then I add on a little tiny bit more to it, and you're like, no, it's going to be definitely a little bit more than 4 and a third. It looks like it's going to keep adding on, but the successive additions that you're going to keep adding on are going to get smaller and smaller, and they're only going to add on a very insignificant amount to the decimal. And this number will converge or limit out as it heads to infinity to probably where? You got a probably good guess? I think it might be like 4.5. Does that seem like a reasonable guess? It's bigger than a third, but it probably is not going to make it to a half. Now, how can I discuss that or see what it should come close to? Well, let's see. What should it be? Well, the formula for an infinite series, now if it's infinite and it's going to infinity, and it turns out that the r is between -1 and 1, okay, then we can use this little formula. It says a sub 1. You take the beginning term and you divide it by 1 minus r. This is the infinite sequence or infinite series for a geometric series, okay? It's going to coalesce to this particular number. Now, if I start to look at this one, maybe just a guess of where it's going to be, you're like, well, but just between these 3 integers, it's already 7, and now it's 7.5. You're like, man, it's got to be more than 7.5, but it's going to not be much more than that. Let's see what that sum turns out to be. So the sum of this infinite sequence would be the first term, the number 4, divided by 1 minus the rate. Now remember that the rate is always found the same way. Second term divided by first term, 2 divided by 4, or a half. And that would end up being 4 divided by 1/2, and the answer would be 8. And the whole thing would squeeze down and sum up to 8. Weird. That's some weird stuff. But it doesn't boggle the mind too badly in the fact that it should coalesce to a specific limit. And that limit is going to be the number 8. I'm getting a phone call. All right, nothing crazy is going on in that phone call, but let's continue and finish off the last piece of this. Now, another place where you can use this infinite sequence or infinite series concept is that you can actually use the formula to help you decide what the fractional form should be for a repeating decimal. Okay, now this is not one of my strongest topics in all of the things that we do in trig pre-cal, so I'm going to muddle my way through it. So be happy that I can maybe figure it out. Use the sum formula to help you find out what the fractional form is for a repeating decimal. Now, these ones down below don't have repeater signs on them because it didn't show up in the notes. So I'm going to make this guy right here 0.7 repeating. Now that just means that this particular question would be like 0.7777777 blah 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 forever. Now the reason why this falls into this particular category of an infinite sequence series is because that particular fraction definitely goes on forever, but it really truly is the sum of smaller fractions that are being added to each other. So you can really think of it as 0.7 repeating is really 7/10 added on to, now that gets the one that goes right there, but the next one in the next place would be 7/100ths, and another one which would be 7/1000ths, and so forth, all the way down through infinity. Now that's no different than a sequence or a series that's up above that's geometric. It's going by a particular value. Now, if I thought about using this particular formula, I could write it as, what would the sum of this infinite sequence series be? Well, it would definitely be the first term of the sequence, which is 7/10ths, and then it would be divided by 1 minus the rate. Now, that 1 minus the rate is where we're going to basically talk about where this comes from. And that, what would that rate be? Well, it would be the second term divided by the first term, and you would end up getting the specific rate. So 7/100ths divided by 7/10ths would end up being, well, you'd end up getting you get a flip it over 7/100 times 10/7, and I'd cross cancel, and that one would be 1, this would be 2. Holy moly, it's 1/2. Or half? No, I did something wrong. 7/10ths. 10. This would be 10. It'd be 1/10. Ooh, see? I'm messing it up as we go. 1/10. Now, if I started to simplify that, that'd be 7/10ths divided by 9/10ths. And if I inverted and flipped that over, it'd be 7/9. And this is the fractional way to write 0.7 repeating all the way down the line. Now, I don't know if you may have remembered that from elementary school, that if you wanted a repeating decimal, instead of dividing by the tens place, instead of dividing by 10, which would only give you 0.7, you divide by one less than that value, and it gives you the repeating one. So if it turned out you were dealing with 0.8 repeating, you could probably remember that this turned out to be 8 divided by 9. And that would give you the repeating decimal. Now, if you need verification of that, you can find it. You can be like, oh, okay, let's try it. Geez, see if you got something going on there. 8 divided by 9, and you would get something like 0.888 repeating. And the only reason why it gives you a 9 at the end is because your calculator run home's the mama and doesn't know what to do with the rest. Okay? But it does give you the repeating concept. Now, there's a special one. If you wanted 0.9 repeating, it actually boils down to that this is a quirky thing in mathematics. The 0.9 repeating really turns out to be 1. And this is like one of those phrases that you learn that 1 is really the same as 2. It's a falsified theorem in set theory, and it's referred to as the axiom of choice. If you go to college, they might explain this a little bit clearer about where this particular idea comes from. Maybe it might be something that you could research and come up with some ideas about it. It's just a funky thing that one shows up as a funny deal. Now, if I was going to repeat something that ended up repeating in multiple places, then how do I deal with that particular kind of division? Now, the easiest way to deal with this is if both of them are being divided by it, then it's going to be the whole term that's underneath the bar, right there, 89. And instead of dividing by 100 in the hundreds place, you do one less like you did with the 9, and you would divide by 99 is what it's going to be. Now, it's really a lot easier when you have to divide ones that have a specific value where both things are being over the top of one another. It turns out that it's a little bit more complicated when it turns out that there is some repeated, but some not. Like, say, for instance, I wanted the 245 to come up, or 2.45, but the 45 to be repeating going all the way down. So basically my answer would be 2.45, 45, 45 down the line all the way into infinity. Well, how do I get this 4-5 to completely keep repeating itself? Now, there is a little Worrell trick to this. And it took me a while to remember it because it was last year. And Mrs. Worrell found a really cool little technique, and that is that whatever you have underneath the repeater. If there's something outside of it, see the guy outside of the actual repeater? You have to think of the whole entire number as like 245 is what you're basically going to think of it as. But since there's a guy on the outside, this is what I have to subtract from 245. So I'm going to take the original 245. I'm going to take away 2 from it because that's the one integer that's sitting out here on the outside, which would be a total number of 243. Now that becomes the numerator of your fraction. And the denominator turns out to be what the value is of the repeater. Well, this repeater goes out to the hundreds, and since both of them are being repeated, there's going to be a 99. Now, I always looked at the nines, meaning that there are 2 repeaters, is what that basically is saying to me, and it gives you 2 different repeater concepts. I'll explain that in a second when we do a different one. So 243 divided by 99. Let's see if the Worrell trick works. 243 divided by 99, and I get 2.454545 all the way down the line. Okay, now the best way to try these is to try a few of them so that you get the basic idea. What if I was dealing with 1.17, but the 7 was the only part that was going to be repeated? Again, the key is to look at it as a full number, which is the number 17, and subtract from it the one thing that is not getting repeated, which is in this case a 1. All right. Now, if it was several things out here like 485, you'd put 485, whatever it is. But that's going to be the number 16 divided by. Now, this is going to be a little tricky right here because this is in the hundreds place. But since I don't want to use 99, because that would mean that there are 2 things being repeated. So what I do is I end up going to 90, which is below the hundreds place, and it only is going to repeat 1 value. So 16 divided by 90, and you would end up with something like, let's see here, let's see if it works. Cross your fingers. 16 divided by 90, and you'd get a number of 0.1777, and the 7s repeat. Now, I've been trying to look at like several different examples of this so that I could come up with better stuff to it, or ones that would make more sense. And I'm going to, I wish I could go down a little bit further. I'm going to try and write a couple of them down here below, just a couple more examples so you get the idea. And I like to show ones that have like a similarity between them all. So like, what if I did 0.625, and I'm going to use that one as a multiple examples, but I was going to do all of 6.25. Everything's going to repeat. So it's going to be 0.625, 0.65, 0.65 all the way down. Now, there is nothing in the front of this one to actually subtract from it. So it would be 625 divided by, and you're in the tens, hundreds, thousands place. So this would be 999, meaning that there are 3 things to repeat. Now let's check that to make sure that that one worked. 625, clear those guys out. 625 divided by 999, and you would get the same repeater of 625. Now, what if I changed that question just slightly and I changed it to 0.625, but I only wanted to repeat the 2 and the 5? Well, if I'm only going to repeat the 2 and the 5, then it would make sense that I probably want to do 625 minus whatever is in the front that's not being repeated, which is a 6. So I'm going to go minus 6 for my numerator. Well, that would be 625 minus 6 would be 619 divided by, but I'm still down here in the thousands place, but I'm not repeating 3 things. I'm only repeating 2 things. So I'm not going to put down 3 nines. I'm going to put down 2 nines. Now, let's see what we got here. 619 divided by 990. And that answer, check it out. The 25s are the only thing that end up going. Okay, now let's do this last one example. What if I wanted to do 0.625, but the only thing repeating is the number 5 is all it's going to be here. Well, that's going to be 625 still. It's whatever the number is minus whatever is not being repeated, 62. And that answer on the top, ooh, I don't know what that is. I haven't figured that one out. That's 563 divided by, and again, I'm out here in the thousands place, but I'm not going to divide by 990 or 999. I'm going to only divide by 900 because I'm only repeating one concept. Let's see if that guy works out. 563 divided by 900. And it turns out that that's the technique that works the easiest. Now, what I want you guys to try is try one for yourself. What if I had 10.125, but I wanted to repeat the 2 and the 5 from it? I'm going to get a little pause right here, give you a second. Try it out on your own, and then I'll do it for you in just a sec. All right, here's what I ended up getting, and I think it's pretty solid. We've got the 10.125, the whole number written all the way out, and then ultimately subtract from it 101. Now, the 101 comes from the 3 values that are out in the front that are not being multiplied or not being repeated. So ultimately, that's what we got to subtract right out. Just take that part and subtract it off. 1024 and 990 because we're repeating 2 different deals. And check it out. It works every single time. I will just tell you, Miss Worrell, she was a genius. Okay, I'm going to give her a little bit of kudos right here because that lady, she is smart. Okay, if you have any questions on these, please don't hesitate to remember to watch Miss Merzak's video on the homework hints tonight and give them a try. Guys, keep pushing forward. We're going to get good at this stuff, and you guys are going to be ready for calculus next year.